So again, today we're going to be focusing more on integration. Now, so far, I've been nice to you guys with integration, including your homework set. I gave you integrals over square regions. X is between 0 and 2, and Y is between 1 and 3, or 0 and 2. Or, you got nice little square regions on that thing. And when we did this stuff, so if I come over here and focus on this material, this is what we did last time from a Riemann sum perspective. We had nice little square regions, and we picked particular points on this guy to figure out estimating the area in the curve. But the last thing that I did not get to was this. And let me get my little pen out here. I want you guys to do this one. So we did this estimate of the volume thing here, and then we had a part B and part C. Did I get to part D? I think I ran out of time on part D. Find the exact volume under, this was our equation. Z was equal to 100 minus x squared minus 3y squared over the region R, which was 0 is less or equal to x less or equal to 2, and 0 is less or equal to y less or equal to 2. And again, to remind you what we did last time, we want to estimate the volume by dividing R into 4 rectangles, and we use the lower left hand corner to estimate, and we kind of did a Riemann sum on that guy. And then we did the same thing, but this time we chose the sample points to be the upper right hand corner and estimate that. And then we got a better estimate by averaging the two together. Okay, but let's do the problem. Here it is. Find the exact volume of this guy under the find the exact volume under the curve. Z is equal to 100 minus x squared minus 3y squared over the region R from 0 to 2 for x and 0 to 2 to y. Well, what have you learned? Well, when I used to integrate in calculus 1, I got area under the curve. But now that we're in it was calculus 2, actually. When I integrated, I got area under the curve. When I in calculus 3, I do a double integral over a surface, and I get the volume under the surface. So what we're talking about here is to calculate the volume. You do a double integral over a particular region of some function f of x, y, dA. This is how you calculate volume. This is your traditional formula. This would be the formula for the volume under your surface. Z equals f of x, y over whatever region you got. The region we have is this square region from 0 to 2 on the x and 0 to 2 on the y. My function z is 100 minus x squared minus 3y squared. So this is going to give me volume is equal to the double integral of 100 minus x squared minus 3y squared. And the dA would become dx or dy. And it's your choice on what you want to do. I'm a big fan of doing dy dx's. So I did dy first, then dx. But my bounds for the dy were from 0 to 2. So it's from 0 to 2. And the bounds for the x is from, so my bound on the dx would be from 0 to 2. So let's calculate this guy. Now, how do you do a double integral? Well, a lot of the times, if you can factor the problem in terms of functions, in terms of x, functions in terms of y, that's great, and you can integrate each one. But when you got something intermixed, you work inside to outside. The inside is the integral of 100 minus x squared minus 3y squared dy. Y is the variable. So if y is the variable, x's and numbers are considered to be constants. So what is the integral of 100 with respect to y? That would be 100y. Minus what is the integral of x squared with respect to y? X is considered to be a constant. So integrate a constant with respect to y would be a constant times y. So that would be x squared y minus what is the integral of 3y squared with respect to y? Now that's a y variable with respect to y. So the integral of 3y squared is y cubed. And then I put my bounds on this thing from 0 to 2. And remind yourself, this is y going from 0 to y going to 2. Now we use the original fundamental theorem of calculus, plug in top minus plug in bottom. And so we're working again on the inside, so plugging in top, this would be 100 times 2 minus x squared times 2 minus 2 cubed. I've plugged in top. Remember, we integrated with respect to y, so we'll replace the y variable, plug in top, minus plug in bottom. Y is 0, so that's 0, that's 0, that's 0. Enjoy plugging in 0, pretty much kills off all my terms there. So now I'm going to clean this up. Here we go. 100 times 2 is 200 minus 2x squared minus 2 cubed is 8. So 200 minus 8 is 192. So this is 192 minus 2x squared. Now you got to do your outer integral. So bring that into it. The integral from 0 to 2 dx. So cleaning this guy up. So this is the integral from 0 to 2 of 192 minus 2x squared dx would be equal to the integral of 192 with respect to x would be 192x minus the integral of 2x squared is going to be 2x cubed over 3, evaluating from 0 to 2. Fundamental theorem again, plug in top minus plug in bottom. This is 192 times 2 minus 2 times 2 cubed over 3 minus plug in bottom. When I plug in 0, pretty much I get 0. So this is 192 times 2, which is 384 minus 2 cubed is 8 times another 2 makes it what, 16 minus 16 thirds. So 384 minus 16 thirds is, I get 378.6666667. And I went decimals on this. I can make it into a crappy fraction if you want me to. That's really doesn't help us out much. 1,136 thirds. Okay, and this of course would be units cubed. So we got for our answer, and again, just to save myself some time and some space, I'll recopy the problem down here. But I got for the answer 378.6667 when I integrated this thing. Does that make sense? So there's my answer. And the reason why I wanted to show you this answer was I wanted to go back and look at these two problems when we did our point estimates using Riemann sums. In the lower left-hand corner, I got 392. The upper right-hand corner, I got 387. The thing's on a slant, so it's going down. But the exact area in the curve is 378.66667. Does that make sense? So it's right there where I'm thinking the answer should be. I didn't know exactly what the exact answer is going to be until I actually integrate it, but it fits the mold. And when I average those two together, I got 376. The exact answer is 378 2/3. Does that make sense? So just kind of want to tie that one together with this particular material, but then let's do another problem. Again, practicing your integral skills. So here's another example right here. Pull it up for you guys in the back there. You guys can see it. I want you to evaluate this. The integral of, the integral from 0 to 1 of the integral from 0 to 3 of 4x squared times y cubed dx dy. This time I switched it up. Dx dy. Order matters. Okay. So with this one, I mean, officially I could if I wanted to, because I have strict multiplication of my variables here. We can use one of our classic theorems and break it up. You could, if you wanted to, you can integrate this guy and basically break up integrals, because this is a product, 4x squared times y cubed. And I can pull the x's together. That would be 4x squared dx. and then times the y's. This is y cubed dy. This is dx. Dx is on the inside bound, so those bounds would be from 0 to 3. This is dy, that's your outside integral, outside bounds is from 0 to 1. And you can integrate this guy and integrate this guy and multiply the answers together. Only because the function that we gave you was a product of x's times y's. And that last one I did, I had the x's intermixed with the y's being added and subtracted. You can't factor that one out. Does that make sense? But I'm not a big fan of doing this. It's just a theorem that we can actually do this to, because 99% of the problems we're going to give you, these variables are going to be intermixed. X squared times y plus cosine y times e to the x squared times y cubed. You know, all that stuff intermixed. You can't break this stuff up. It's got to be a strict product where you got x's times y's times a constant, and you can pull the constant with either one you want to and basically do a product of these guys. But for me, I want to get you guys, because I know where you're headed with this stuff, getting used to doing it the more traditional way. When I got a double or later on triple integral, I'm going to work inside to outside. You work on the inside integral first. That's why order matters. So inside first is this guy here. It's the integral from 0 to 3 of 4x squared y cubed dx. That's the inside. Constants and now y's are going to be variables because I'm integrating with respect to x. So integrating with respect to x, 4 is a constant, leave alone. The integral of x squared is add 1 over add 1. That would be x cubed over 3 times y cubed is a constant, and we're integrating with respect to x. And this will be evaluated from 0 to 3. And I always put little x equals. You don't have to do this. It's not required, but it reminds me of who the variable is. Especially when I do multivariable stuff, sometimes I can get lost on reminding myself who the variable is. Okay? Plug in top minus plug in bottom. So this is 4/3. Plug in x is 3. That would be 3 cubed times y cubed minus 4/3 times x is 0 cubed times y cubed. Because x was 0 being multiplied, that part goes away. 3 cubed, I believe is 27. Divided by 3 is 9 times 4 is 36. So this turns into 36 y cubed. And now I put my outer integrals on there. The integral from 0 to 1 dy. I worked inside the parentheses first. Now integrate. What's the integral of 36 y cubed? Well, 36 is a constant. Integral y cubed is add 1 over add 1, y to the 4th over 4, evaluated from 0 to 1. And so when I plug it in, let's see here, 4 goes into 36, what, 9 times? 9 y to the 4th, evaluated from 0 to 1. Again, fundamental theorem of calculus, plug in top minus plug in bottom. 9 times 1 to the 4th minus 9 times 0 to the 4th. And I end up getting pretty much 9. Does that make sense? I also noticed something rather. On that last problem I did, I put it up here. I put on the other ones, I didn't write on this one, but units cubed. Why would I put units cubed on this integral, but not put it on this integral? As you mentioned, this one mentioned the word we're calculating the volume. This one, I don't know what I'm calculating. I mean, this could have been some interesting rate of change or something or other. I don't know. So if I don't know what I'm dealing with, I don't typically going to put the units. I can still integrate the thing. Okay. I only put units on a word problem that I'm actually given or whatever. Does this make sense? Now, if you don't believe me on this thing, you can come over here and let's just save a little bit of time and some effort here. What's the integral from 0 to 3 of 4x squared dx? Well, integral, that would be 4/3 x cubed, plug in top, plug in bottom, but I'm going to use my calculator on this thing. So math number 9, just like we did in calculus 2. Double check my answers. Integral from 0 to 3 of 4x squared dx. I got 36, and over here, my second one was math number 9. Integral from 0 to 1 of y cubed, instead of y, we use x's again, x cubed dx. And I end up getting 1/4. And if I take 36 times 0.25, 1/4, I get 9. And that's basically multiplying these two answers together. And I get my answer that way. Only because this function we played would factor into X terms times Y terms. If it doesn't do this, you can't use this properly. Does that make sense? Did I lose you guys anywhere? Questions? All right, keep going then. Based upon this, again, how can I give you web worky kind of problems or test questions or whatever? Try this question. It says this. If the integral from 3 to 4 of f of x dx is -1, and integral from -3 to 2 of g of x dx is 5, then what is the value of the iterated integral, double integral over your region D of f of x times g of x dA, where D is 0 is less or equal to x, which is less or equal to 4, and -3 is less or equal to y, which is less or equal to 2. Well, again, it's all about how I express the problem. This was an interesting function that is a product of terms of functions in terms of x and functions in terms of y. So there should have been a y right there. Okay. So you want to integrate this guy, but this is in terms of x and this one's in terms of x. But once you integrate, this is our point of this problem. Who cares what the variable is? If I integrate from 3 to 4 of f of x dx, I get -1. I can tell you something else. The integral from 3 to 4 of f of y dy is going to be -1. The integral of f of t dt from -3 to 4 is going to be -1. It doesn't matter what the letter is. You integrate, then you plug in top minus plug in bottom. The letter at the end of the day, the variable, doesn't matter. Okay, so I wrote both these two guys in terms of x. But I don't want you to do this double integral of over your region D of f of x times g of y dA. And it's your choice whether you want to do dA being dy or dx. You can write it like this. I would be the double integral of f of x times g of y. And let's say we're going to do my famous dy dx. So if I did this dy, the inner integral is y. Y runs between -3 and 2. And then dx at your outer integral works from 3 to 4. Okay, but because my function is a product of variables, functions with variables in terms of x, times a functional variable in terms of y, and it's a product that I can separate according to our theorem, this is equal to the integral from 3 to 4. This was times f of x dx times integral from -3 to 2 of g of y dy. Because it's a product, things of x is times things of y, you can break up the interval. It's a very special case, only works when you have an actual product. Does that make sense? And like we just mentioned, it doesn't matter what the letter is. Yes, so the integral from 3 to 4 of f of x dx is going to be -1. So the integral from 3 to 4 of f of x dx, yep, that's going to be -1. However, the integral from -3 to 2 of g of y dy, well, we're given the integral from 3 to 2 of g of x dx is 5. So, but I'm telling you, it doesn't matter what the letter is. That will also be the integral from -3 to 2 of g of t dt, still going to be 5. And you can change the letter to something else you won't, like y. -3 to 2 of g of y dy, it's still 5. It doesn't matter what the letter is. So this part is going to be 5. So the answer to my question is -5. It's working my theorems that if I can break it up, that's great. But it's a very special case that you got a function that's a product of x variables times a product of y variables that you can separate. That's a rare thing. But if you do that, you can just basically break up your intervals, integral of the x terms times the integral of y terms, get your total answer. Okay. So do this one. Calculate it. What is the integral from 4 to 7 of the integral from 1 to 6 of x times y times e to the x plus y dy dx? Well, again, this guy, can you break up the x terms times the y terms? If you can, you can break it up into two different intervals. If you can't, well, great. This one, with that e to the x plus y, that thing is intermixed. So I may have to integrate it the old-fashioned way. And that's the integral with respect to y, and that's going to be y times e to the, man, that's going to be a royal pain. But I can do it. But what you should note is this. Note. E to the x plus y is the same thing as what? E to the x times e to y. Why? Because when you multiply, you add exponents. So if you know your algebraic properties, they can come back and be very advantageous here. So this will turn into the integral from 4 to 7 of the integral from 1 to 6 of x times y times e to the x times e to the y dy dx. And because you now have broken it up into a product of just x terms times y terms, you can group together the x's and group together the y's, and you can get this. Now, be careful of your bounds. dy is on the inside. So let's focus on the y's. So this will be integral dy. The y's are from 1 to 6. With me? What are the y terms? It is x times y, e to the y. Y times e to the y. Get my letters out right. It's y times e to the y. With me? The x times e to the x, when you integrate with respect to y, are considered constants. Where do constants get to go? From my integral. So this would be in front of the integral, e to the x times x. And because these guys are constants, you can just integrate this guy, and you might as well pull the dx and the integral still out front. These are x's, so that's going from 4 to 7. So you can see how the formula was developed. Yes. That'll be e to the x times e to the negative y. Plus, so it'd be exactly the same. Just keep the sign with it. No, so yeah. Does that make sense? All right, so now I just got to evaluate these two guys. Now, this is the part that should scare you. All right, so let's integrate this guy. Let's integrate from 4 to 7 of x e to the x dx. And then we're going to integrate down here, the integral from 1 to 6 of y e to the y dy. Again, this was a very special function. I want to emphasize this. Most problems I'm going to give you, it will not be like this. I will give you like one of them. Hey, I can break this up and I'll save a little bit of time. But my question now is back to calculus 2. What is the integral of x e to the x dx? Well, the integral e to the x is e to the x. But x times e to the x doesn't work. Try u substitution. We're going to let u equal 2. Well, if you let u equal x, the exponent on the e, that's just stupid because it doesn't change anything. You remember that one. U equals x, du equals dx. It turns into integral of u e to the u du, and it doesn't really change anything for you. So u substitution is not working for me, and it's a product. You remember what technique of integration you should use when u substitution, your number one technique of integration, does not work, and it's a product. Outstanding. Integration by parts. Yep. All coming back to scare you. Integration by parts. That was the integral of u dv equals uv minus the integral of v du. Basic rules. Number one technique of integration is u substitution if it's not a basic rule. And if u substitution doesn't work and you can write it like a product, integration by parts. Integral of u dv equals uv minus the integral of v du. Here, I'm going to let u equal to the x. This is integration by parts, not u substitution. dv would be the rest of it, which is e to the x dx. This means that when I take my derivative du, derivative of 1 with respect to x would be 1 dx. And v, the integral e to the x is e to the x. So here's my parts. I plug into my formula. It becomes u times v, which is x times e to the x, minus the integral of v, which is e to the x times du, which is dx. And literally see the integration by parts, be plugging the parts into my formula. Now, what's the integral e to the x? You can integrate that guy. So this is x, e to the x, integral e to the x is e to the x, but instead of plus c's, we got bounds from 4 to 7. According to the fundamental theorem of calculus, you plug in top minus plug in bottom. This will be 7 e to the 7th minus e to the 7th, plug in top, minus 4 e to the 4th minus e to the 4th. Let's clean that up. What is 7 e to the 7th minus e to the 7th? Outstanding. 6 e to the 7th. They're both e to the 7th. Just add a coefficient. 7 minus 1 is 6. 6 e to the 7th minus, what's 4 e to the 4th minus e to the 4th? 3 e to the 4th. I'm sorry, it doesn't get much better than that. There it is. Okay. So there's one answer. I'll just dot it right here real quick. Now let's integrate this guy. What is the integral from 1 to 6 of y e to the y? Well, just like the last one, it didn't work in terms of it's not an integral formula I memorized. And it's a product. New substitution doesn't work. And it's a product. So once again, I do integration by parts. So I would let u equal to y this time. That means du equals dy. That means dv equals e to the y dy. And when you integrate e to the y with respect to y, you get e to the y. Plugging my parts in, integral of u dv equals uv minus integral of v du. This will turn into u times v, which is y e to the y, minus integral of v, which is e to the y. dy is du is dy. This is y e to the y minus e to the y, evaluated from, no plus c's on this one, 1 to 6. So plug in top minus plug in bottom, that'll be 6 e to the 6 minus e to the 6 minus 1 e to the first minus e to the first. What is e to the first minus e to the first? That goes way there, 0. What is 6 e to the 6 minus e to the 6? 5 e to the 6. So there's my answer for that guy. But wait, the question was the integral from 4 to 7 of the integral from 1 to 6 of x, y, e to the x plus y, dy, dx. And what's that going to be equal to? Well, turn to the product of these two problems, these two functions. The first one I got was 6 e to the 7th minus 3 e to the 4th times the second one, which is 5 e to the 6. There's my answer. However, for those people that just want to clean it up because you should have the ability to do so, what do I get? Well, distribute 5 times 6 is 30. What's e to the 7th times e to the 6th? Well, when you multiply, you add exponents. That's e to the 13th minus 3 times 5 is 15. E to the 4th times e to the 6th, you add exponent, that becomes e to the 10th. And that would have been my cleaned up version of my answer. Two things. Number one, if, and it's a big old if, most of them I can't. You notice that even with the square balance, I've always worked inside the parentheses, held the one variable constant, integrated with respect to the other variable. But if you can factor your function into something in terms of x's times something in terms of y's, like we did here, you can integrate the product. Integrate the first one times integrate the second one with respect to x, one with respect to y, and actually get your answer. The other thing that should scare you to death is, that's right, integration by parts is going to come back and haunt you. When U substitution doesn't work, that's what you got. All right. But what if you don't happen to have nice bounds? Okay. So what I mean by that is this. Get my little bit papers together here. All right. All right. Section 12.2. Double integral over general regions. General regions versus square regions. So I'm going to go back and pull some stuff that I taught most of you guys when you had me for your Calc 2 professor. When I integrate, and I was doing like dx's and dy's, I always did this concept of top minus bottom and right minus left. Top minus bottom, right minus left. That's coming back to haunt you once again with this material. Okay. So with that, let's take a look at this stuff. Now, when I have a particular integral over a particular region D of some function f of x, y, and we're doing dA, that's either dy dx or dx dy, and order matters, okay? If you look at this guy right here, look at your region. I've got, out of my region D that I'm trying to integrate over, I got a top function, y equals g2 of x, over a bottom function, y equals g1 of x. g2 of x is on top, g1 of x is on bottom, okay? So, remember from calculus 2, when I integrate with respect to y, it's top minus bottom, top over bottom. It's the integral of y equals top on the upper bound and y equals bottom on the lower bound. That's dy. And if I integrate with respect to x, x on the upper bound would be x equals right, over the lower bound, x equals left. Okay, so you got your top bottom, that'll be dy. See, because I know when we integrated, Dr. Taylor, we never did the integral with tops and bottoms. No, you looked at the region and you did integral, and then you had top function minus bottom function when you plugged it in. Now we're rewriting this with integrals. So this is what you need to remember and notice. When I integrate with respect to y, it's y equals top, it'll be your upper bound, y equals bottom is your lower bound. And yes, you can have functions in terms of bounds, not just numbers. Everything we had to date, we've been integrating over square regions from 1 to 3 and from 2 to 5 or something like that. Nice square regions, not anymore. We're doing general regions. So this integral for dx is left, sorry, x equals right on top, x equals left on bottom. Now that's still concept of calculus 2. So if I was going to do this problem right here, here's the deal. Because I have a distinct top function on of my region D, I have a distinct function that defines the top, g2 of x. I got a distinct function that defines the bottom, y equals g1 of x. I would want to integrate with respect to y first. So this would be integrate your original function, f of x, y, whatever that function is. It's all about the bounds. This would be the integral from y equals g1 of x to g2 of x. G2 is on top, g1's on bottom, so you read it from bottom to top, g1 of x to g2 of x. I did dx first, and then I do dy. Sorry, excuse me, I did dy first, now I'm going to do dx. You got to define over your regions. So your last integral, as you work from inside to outside, your last integral should always have numbers. It defines the region. So this was the top, this was the bottom. This is what we're trying to integrate through. So when I do dx, it's right, left. But the last integrand should have numbers on the bounds. So this would be, the left would be A, the right would be B, numerically x equals A to x equals B. And this is how you would set up your integral. Okay? But look at it. It's a double integral, some weird function, f of x, y. I will give you that. I did dy first, and on the inside integral, I'm integrating with y's, and I'm going to have functions in terms of x, because x is, when you integrate with respect to y, are considered to be constant. And then I integrate dx, and when I integrate dx to create my region, these will be numerical values, so it cuts off the region. So at the end of the day, you're going to have a numerical answer. After you integrate, you plug in top minus plug in bottom with constants, and you end up getting the actual solution, numerical value. But if I switch this up, however, if I give you a different region, this region D here, instead of being tops and bottoms, I got regions rights and left. There's this nice little parabolic region over here, x equals g2 of y. It's in terms of y because it's not a function. And over here, I got x equals g1 of y. And instead of distinct tops and bottoms, I got a distinct right, left, okay, of my region. So if I'm once again going to integrate, find the integrated integral, double integral over d of f of x, y, dA, what order should I take it in? Well, the order that I should take it in, because I have a distinct function defining the right and a distinct function defines the left, right, left, that means you should do that dx first. So this would be the integral of f of x, y with dx, and it will be what's the function on the right is g2 of y, that's be at the top integrand. The function on the left will be g1 of y, that's the function defines the left. And then here's the deal. That's dx, right minus left. So it's the integral from g1 of y to g2 of y of f of x, y as you read it from bottom to top of dx. And then I'm going to integrate that with respect to y. Y is top bottom, but x is your variables. Y is going to cut off the region, so this will be numbers. This will be dy, so these have to be y numbers. The y numbers are from the region from C, integral from C to D. And again, this will give you a numerical value of integrating this function over this region. So with that being said, let's do a problem. Something completely different. Here we go. I want you to integrate over the region D, the double integral of x times y dA, where D is the region bounded by the geometric shape, which will be a triangle when we're done, bounded by the vertices 0, 0, 2, 0, and 0, 6. So you want to draw the region here. 0, 0, I can handle that. That's the origin. X is 2, y is 0. So 2, 0 would be right here. Here's 2. Here's the point. Like we said, this is the point 2, comma 0. The other one is 0, 6. So I'm going to put it up here. This is it up here at 6. Here's the point 0, 6. This triangular region is the region we are trying to integrate over. Okay. Here's the deal. I didn't give you any functions at all. You're going to have to come up with your own. So if I'm going to integrate this guy, this integral of x, y, I got to decide who am I going to integrate with respect to first. Now, as I look at this, I see this is a function, this is a line. I can come up with the equation of that line. What would that line be? Well, I need the slope, which is the change in y over the change in x. That would be change in y would be 6 minus 0 over the change in x, 0 minus 2. According to my math, that's -3. Use my point slope formula, y minus y1 equals m times x minus x1. Pick a point, I like the point 0, 6 here. Y minus 6 equals -3 times x minus 0. Solve for y equals -3x plus 6. There is the equation of the line. I had to come up with it on my own, but there it is. Since this is a function in terms of x, the way I would integrate this, I would do dy first. If I do dy first, these will be y numbers, and these are regions. So if I do dy, it's top, bottom. What's on top is the function y equals -3x plus 6. What's on bottom of this region? That's an equation right there. What is that? The x-axis, y equals 0. So it's from 0 to -3x plus 6. Then I'm going to do dx. But I got to integrate over my region. So this is dx, this is right, left, but you got to define the region. So the outer integral will always have numbers to define the region. So what's that going to be between? X numbers between 0 and 2, from 0 to 2. These will be x numbers from 0 to 2. So this turns into the integral from 0 to 2 of the integral from 0 to -3x plus 6, xy dy dx. Let's evaluate this guy. Well, I'm going to integrate with respect to y. X is constant, y, integral of y would be y squared over 2. So this would be x times y squared divided by 2. Evaluated from 0 to negative 3x plus 6. And again, you're plugging, these will be y numbers. We're replacing y. Plug in top minus plug in bottom here. I end up getting x times negative 3x plus 6 squared divided by 2 minus x times 0 squared divided by 2. Well, that part's going to go away. So this is equal to x over 2 times negative 3x plus 6 squared. Well, I'm going to FOIL that out. So that's x over 2 times negative 3x plus 6 times negative 3x plus 6. And I'm going to FOIL this out. So this is x over 2 times negative 3x plus 6 and negative 3x plus 6 is 9x squared. Outer negative 3x plus 3x times negative 6 is minus 18x. 6 times a negative 3x is another negative 18x, and 6 times 6 it becomes a plus 36. Cleaning this up, this gives me x over 2 times 9x squared minus 36x plus 36. Distribute the x's, the x over 2. So this gives me, let's see here, 9 halves x cubed minus 2 goes in 36 18 times 18x squared plus 18x. So this now turns into the integral of 9 halves x cubed minus 18x squared plus 18x dx from 0 to 2. So integrate x cubed with respect to x, that'll be x to the 4th over 4. That'll be 9x to the 4th over 2 times 4 is 8. Minus integral of x squared is x cubed over 3. 3 goes to 18, what, 6 times? It'll be 6x cubed plus integral 18x, it'll be x squared over 2. 2 goes to 18, 9 times, it'll be 9x squared, evaluated from 0 to 2. According to the fundamental theorem of calculus, you plug in top minus plug in bottom. 9 over 8, 9/8, 2 to the 4th minus 6 times 2 cubed plus 9 times 2 squared. Minus plug in bottom, plugging in 0, you pretty much get 0. And again, just using my handy dandy calculator to get this. This would be 9 divided by 8 times 2 to the 4th minus 6 times 2 cubed plus 9 times 2 squared, which is 4. I can do that kind of math, but there we go. And I end up getting the answer of 6. But wait, we're not done. I only got 30 seconds left. Let's do this. What if I switch the bounds and did this? The double integral of x, y, then I do dx, dy. Well, here's the deal. The region is exactly the same. But your line, instead of you're going to do right and left, you got y equals negative 3x plus 6. X is going to be equal to y minus 6 divided by a negative 3, or y equals negative 1/3 y plus 2. Okay, so there's your line now, but that's on the right. X equals 0 is on the left. So now your bound ends up becoming this. Let me blow this up. You guys can see this in the back. If I do dx first, these are x bounds, and it's right, left. Right would be negative 1/3 y plus 2. X equals 0 is on the left. And then your dy bounds, y's are running between 0 and 6. 0 to 6. And you know, if I integrate this guy, a second way of doing this problem, you know what your answer is going to end up being equal to? And there's only one answer when we love math. But there's a different way. And then I integrate with respect to x squared over 2, plug in top, my plug in bottom, pull it out, then integrate it again. You're going to get 6 again. So this is the idea. And this is the idea of also switching bounds. We'll study more on this concept next time, as well as looking at something called polar coordinates, a different way of integrating stuff. See you guys on Wednesday.